Straight lines have equations, I hear you shout from the rafters. Well, firstly, please don't shout at me. There is no need. I am not deaf. And secondly, yes, I know, keep it a secret. If it gets out there will be way too much of a panic. Markets will crash, and the fish prices will just soar through the roof. But yes, straight lines have an equation. Really? Well, let's look at some important language first, so we can get the exciting stuff over and done with, and then talk a little bit more about why do equations have straight lines. This is the language I'm going to pretty much cover in this video with regards to gradient, intercept, gradient form, the words parallel and perpendicular, many of which you should already have met before. So we've already come up with the idea previously that a straight line has a gradient. Here is a straight line and it seems to be sloping up, and we've decided that that would have a positive gradient, and lines that slope down would have a negative gradient. This would be worked out using a calculation by using a formula that gradient, which we've decided, thank you to our good friend Barry, is given by rise over run, or I suppose more formally, y2 minus y1 over x2 minus x1. Remember that formula? So we have a gradient, but how do we now make this an equation? You know, an equation's got to have numbers and letters and all sorts of stuff in it. Well, it very much bases on this idea of m. So if I look at a real world example, and here is one I've prepared earlier, we have a straight line that seems to be passing through on my y-intercept a point of 0, 3. Well, let's just write that down for a second. We know that 0, 3 is basically a x value and a y value. So it suggests that that has a y value of 3. Now that actually is incredibly important to us because it also has a name. When it crosses through the y-axis, the point it crosses through is called the intercept. And that intercept in this case would be given the value of 3 because that's the number it crosses through on the y-axis. It's crossed through at y equals 3. Now Barry's been at it again because as usual we're trying to work out how it is we name things. What could we have intercept abbreviated to? Yep, I know. You think I? No. Barry's decided that an intercept is going to have the letter C. Yeah, well, at least the letter C tends to appear in there. If you look at the word gradient, M doesn't appear in the word gradient at all. Not in my language anyway. So we can now say that my intercept is 3. And someone somewhere in a previous life, or in a previous lesson at least, has decided that actually we can define a straight line using an equation. And what it says is the y value of my equation is equal to mx plus c. Y is equal to mx plus c. Now that thing there is incredibly important, right? But what do each of the letters mean? Well, this y means my y value. That there is a rule to get from my y value, or get to my y value. And what is that rule? It says, well, to get to the y value, I take m, which we already now know is gradient. And we multiply that by my x value, and I have to add on my intercept, my c value. So in looking at an equation, we should be able to see what the gradient is and what the intercept is. But I want to talk very quickly about what this gradient means, this gradient of 2. Remember, gradient is equal to up divided by across. And if we now look at that and put it equal to, then we find out that the gradient of 2 just sits there. But we know that any whole number can be turned into a fraction by dividing by 1. That hasn't changed the value of my whole number. 2 divided by 1 is still exactly the same as 2. But now we can talk about gradient a little bit more sensibly. Because what that seems to suggest is that a gradient of 2 means that for every 2 units I go up, I go 1 unit across. So for every 2 units I go up, I move 1 unit across. Now that actually helps us a little bit in terms of being able to plot this thing if we were here now talking about plotting graphs. Because what we would do is imagine I've got a point here, and I know it's not on a scale, but imagine we have that point. To get to the next point, I would go 1, 2 up, and 1 across, and there is my next point. How would I get from there to the next point? I'd go 1, 2 units up, 1 across, and I do a kissy. And yes, if I then had a nice straight ruler, theoretically speaking, I would be able to join these all together, and that would give me a nice, completely unstraight line. But generally speaking, all I'm saying is if I have a start point, and I know the gradient, I know how many squares across to go and how many squares up to go, I can do that. So like I say, I went up, one across, up 2, one across, and having had 3 points, I was pretty confident that I could then draw my straight line. So the gradient of 2 and this value here are incredibly important to me, right? Because in a way now, what we're saying is this point could almost act as a start point. We know the intercept. We know that actually it starts on the y-axis. And we now know that using this gradient value, right, making sure I've got it in a fraction, I can work out how many squares across I go and how many squares up I go. Confused? Hopefully if I do an example, you'll be a little less confused. So we've already come up with this formula of y equals mx plus c. So again, just want you to know m is nothing more than the value of the gradient. Okay? And c is nothing more than the intercept. The intercept is the value on the y-axis. If I just draw some axes, it's this value here, for example, that it starts on. And the gradient is nothing more than working out a measure of the slopiness. Let's throw some numbers in and see what we come up with. Here we go. Here's an equation. Y equals 2x plus 6. Y equals 2x plus 6. So what does that mean? Well, comparing y equals 2x plus 6 with y equals mx plus c, what do we find? And maths is a massive amount of comparing. Yeah? If you've got a formula and they've given you something that looks like it, then compare it. Obviously, these values here are the same. They're both a y. And these things here are both x's, so they must be the same, which would then suggest that actually we can now say that this must be the same and these must be the same. So I can see from my formula that m equals 2 and c equals 6. Now I should really possibly put positive 6, but we'll come back to the difference in that later. So I now know that this c equals 6 suggests that if I was to actually draw a set of axes, where could I suggest my line starts? Again, I'll come back to that in a moment. Well, yes, here is the value 6, so that is where I could actually do my first value. I could put across here, and that would be my first value. What does this m equals 2 mean? Yep, it means a gradient. We know that gradient is equal to rise over run, and they've told me that's equal to 2. We can turn that into a fraction by making it 2 over 1 because that hasn't changed the size of the fraction, and it means then that for every 2 units I move up, I go 1 unit that way. Right? Why is it that way? Because it's a positive gradient. So I could now effectively go up 2 units, so that would make that 8, and a 1 cross 1 unit there, and we'll assume that's a 1 there, and again go up 2 units to there, which would make that 10 on that axis, and across 1 unit, which would make that a 2 there. And having got 3 points, I could then join these lines together, or these points together. And this is one of the tricks where people go wrong in this exercise. They'll actually think that that cross there is the start. And you'll have to excuse the fact that that doesn't even vaguely go through the line. But it doesn't. This line actually goes on to infinity and beyond. And if any other maths teachers are watching this, I totally apologise for the state of that line. It will get better, I promise. But, as I say, to infinity and beyond. Not wishing to quote Buzz Lightyear, but actually this line, theoretically speaking, goes on and 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 on. So why do we only draw this bit here? Well, we pretty much pretend that our axes act like a picture frame. So what we do is we sort of say, I'm actually only interested in the part of the line that fits between the axes. A lot of information there? Well, sort of, but I suppose the key points is that value there, the 2, is my gradient, and that value there is my intercept. Well, we're pretty lucky if we get everything written then in that form. You know, we've now decided that if I have y equals 6x minus 4, I'm very happy. I can find the intercept, I can find the gradient, and I can probably sketch this graph or draw it. But what if they try and trick us? Because remember, maths is a BFT. And what does that mean? It's a big fat trick. We're there just to try and trick you. Here, that is horrible. That does not look anything like y equals. But it is very similar to what we're trying to look for. This, if we write it out, 2y plus 3x equals 12, has a number of interesting features. It has a y term in it, as did that. It has an x term in it, as did that. And it had a constant term, as did that. So actually, all I need to do is rearrange this. I need to use my basic algebra skills to move things around so that I actually get it into y equals form. I'm going to move things around to get it into y equals. So how do we do that? Well, same old as we've done before. Kissy kissy, the 2 and a y are stuck together. We don't want to separate them, so we're going to move this term to the other side. So that would give us 2y equals 12 minus 3x. Now I know many of you are screaming at the TV screen already going, no, that's wrong, but hold on. Remember, the basic idea is we don't like Q jumpers, so the 12 stays where it is. We don't want the y on its own. We're going to divide everything because the 2 and the y are kissy kissy. And so we want to break up the happy couple by moving the times by 2 over to the other side, and it's going to become a divide by 2. So y is equal to 12 minus 3x divided by 2. Yep, okay, that is a way, but it doesn't quite fit my y equals mx plus c. Well, let's deal with this divide by 2. Now remember, when you've got one number on the bottom of a fraction, you can divide both of the top terms. You can sort of split it up into different fractions. So that now becomes y equals 12 over 2 minus 3x over 2. Well, we know what 12 over 2 is. Y is equal to 6 minus 3x over 2. Ooh, we're getting incredibly close, but not quite. We want this in the form of y equals mx plus c. At the moment, this seems to be written in y equals c plus mx, and we'll worry about that minus sign in a moment. So we're close. All we need to really do is move things around a bit, is to change the order and move this and this around, and we pretty much are back to my y equals mx plus c form. So remember that minus sign belongs to the minus 3, so I can rewrite that as y equals minus 3x over 2 plus 6, and yay, we get y equals mx plus c. So what is my gradient? Well, my gradient turns out to be minus 3 over 2. And my intercept will be equal to 6. So a word of warning about this minus 3 over 2. Remember that gradient is equal to rise over run. So that's rise there, and that's run there. What does it actually mean? Well, in this case, the minus sign means actually rather than going up 3, you go down 3 units, and you will move that way 2 units. So this is a negative gradient, which hopefully if we're moving down 3 and across 2, means our gradient will end up looking a downward sloping line. Yay, this is quite exciting. One piece of information that you need to know, this form here, this y equals 6x minus 4, is called the gradient form. Alright, it's called the gradient form. This form here, the 2y plus 3x equals 12, I believe is called the intercept form, but it's important to know the difference. This is a nice easy way of graphing, which will show you some other point. Well, this part of the video is coming towards an end nearly, but maybe some pre-learning or pre-information for the difference between a parallel and a perpendicular line. A parallel line basically is a line that has exactly the same gradient. That line there and that line there should, in an ideal world, have the same gradient. They are then parallel. But how would we show that with the equation of a straight line? Well, I suppose the trick there is to say the gradients are the same. So y equals 2x plus 6 and y equals 2x minus 3. Hopefully you can see they both have exactly the same gradient. They both have a gradient of 2. The only difference is effectively the intercept, so that's where they start on the y-axis. So these two lines here are parallel because the gradient is exactly the same. If I had y equals minus 2x plus 6 and y equals 2x minus 3, then are these values the same? Nope. There is a minus 2 there and a positive 2 there, which would suggest that actually they are different. So these lines here are not parallel. Are they perpendicular because one's a plus and one's a minus? No. Common misconception. And again, I'll just point out the fact very quickly that a perpendicular line is defined that where the lines are at right angles to each other, right? So between the two of them, there is a right angle. There is a link between the gradient of a parallel and a perpendicular line, but at this moment in time, it's beyond the scope of this video. You can say you're excited by the equation y equals mx plus c. Dinner conversation. Knock yourself out. Thanks for listening.